Hello everyone, my name is Jin. In this video, we'll be doing the KNN machine learning project on the Iris dataset. As usual, we need to import all our necessary libraries. So let's go ahead and run that cell. Then we need to do some data cleaning and processing. First, let's load the data and shuffle the data. And this is our data. So in our data, we have the simple length, simple width, and paddle length and paddle width. And then we need to separate our dataset into training and testing subset. First, we need to determine the percent of data that will be used as training set. In this case, I have defined to be 80%. And then based on that, we calculate the cutoff index. Next, we need to pull the data from the data frame. So let's go ahead and do that. So the training data will be from index 0 to the cutoff index. And the testing data will be from the cutoff index all the way to the end. Let's go ahead and run that. Oh, I'm missing a bracket here. Alright, so we see here our training data has 121 data points and testing has 30 points. And they are all NumPy arrays. Now we need to do some data visualization. So let's visualize our data. I'm using the Plotly Express libraries. So Plotly will give a really pretty scatter plot that we can clearly see how our data looks like. Our dataset has 4 attributes, but we only can plot 2 at a time. So let's first use the simple length and simple width as our x and y. We see that the red, or the iris setosa, is pretty clustered here, while the blue and the green are meshed together here. It's hard to determine which one is which. They are all mixed up. And then let's take a look at our paddle length and paddle width. We see similar things, like red is by itself and green and blue are mixed up right here. But it's obviously better than the previous plot where we plot the simple length and simple width. And then to have more idea of what the data looks like, we plot a 3D scatter plot. And the nice thing about Plotly is that you can actually drag and zoom in, zoom out, and we can reset our view right here. So we see similar things. Red is by itself, while green and blue are somehow mixed together. So now let's build our model. First, we need to have a function that calculates the Euclidean distance between 2 points. So we got point 1 and point 2 as our input, and we loop through each dimension. We should add a square of the difference between each dimension. So let's go ahead and do that. So let's first take point 1's dimension minus point 2's dimension. That's the difference, and then we need to square it and add it to the distance. So we sum up all the square of the difference in every dimension, and then we return the square root. Oh, square root is not defined. So let's import the square root function from mass. Import square root, and we have a testing case right here. So the point 1 is 0, 0, point 2 is 1, 0. The distance should be 1, and it is correct. Alright, next we need to have one function that calculates the most frequent class given k neighbors. I put in a testing case here. We have 3 Iris virginica, and that's 6 Iris setosa, and 2 Iris versicolor. And this function should return Iris setosa. Why? Because it is the most frequent. So let's go ahead and write that function. and it returned the Aries setosa. Next function is the actual KNN. So we got the input points and our training data, and how many neighbors are you looking at. This function will return the label of the input points. So first we initialize the distance. We need to calculate the distance of every single point in our training data to the input points. We already have a function written to calculate the Euclidean distance. So let's go ahead and call that. So the distance will be Euclidean distance. That's our function, and it take the input points and our training points. Okay, and it will append the training data and the corresponding distance. Next, we sort the distance, and then we initialize a list of neighbors, and then we loop through the distance, the first k distance, because the sorting is sorted in ascending order, so the closer point will show up on the top. So we just need to loop through the top k points. That will be our neighbor, and then we need to append the label of the neighbor. Alright, if we remember, in our distance we have a tuple of the points and the distance. So we need to first read index 1 to pull up the training data points. So we got this. So we're reading the first element of the tuple, and it will return the label, and the label is actually showing up as our last element. So we need to have index of 0 and the index of -1. -1 index means the last element, and if we run that, it gives us a naming error. Euclidean distance is not defined. Oh, I think I missed the S here, so let's go ahead and add the S. Euclidean, oh, I forgot the C as well. Oh, it's not, there's no S. Okay, so it's fixed right now, and if we run this testing point using k equal to 1, we got Aries versicolor, and the true class, the ground truth, is Aries versicolor. So we're all good here. Alright, next we need to make our prediction and see how are we doing. Let's first try k equal to 1. Run each point to our KNN model. So we got KNN, and our input data will be our row, and then the training data, and k, our k. Alright, same thing for the predict class. The row, training data, and k. Let me delete the space here. Okay, and then let me just run that. We see our training accuracy is 1.0, which means we get all the training points right, and it makes sense, right? Since we're only looking for the code, since k is equal to 1, so we're looking at the point with itself, which always going to be correct. And our testing accuracy is only 0.9%. Let's try increase our k and see how the performance. Let's change it to 10. We see our training accuracy goes down while the testing accuracy stays the same. Let's change it to 20. We see our testing accuracy goes up and our training accuracy go down a little bit. So the point is we want to maximize testing accuracy, right? Because if training accuracy is too high while the testing accuracy is low, it means we have an overfit. Alright, let's say 30. Let's change our k to 30. We see a decrease in testing accuracy and a decrease in training accuracy. Let's change it to 40. An even lower training accuracy, which makes sense. Let's change it to 80. we see the performance go down significantly. So changing the number of k is what we call the hyperparameter tuning. So we have the model, but the model actually change depends on the k. So we want to find the optimal k that gave us the best performance. In this case, let's say 30 actually let's say 20, 93%, which I think that's the highest we see so far, while maintaining a high training accuracy. Okay. Now let's visualize our training result. So this is our training true data, right? Because we have the color as training data. And let's see our result, which is a train prediction. We see we missed some points here, because this point is in the part where blue and green mix together. Alright, now let's look at our testing result. This is our ground truth, and we see much less testing points because we have 20% on testing, while 80% on training. So let's see our performance. We misclassified this one and this one. Since these two are in the middle, it makes sense, and green was all perfect. Hope you like this video. If you have learned something from this video, please hit the like button, subscribe to the channel, and please turn on the notification. I'll be releasing more videos about machine learning and data science. See you guys in the next one.